Welcome, everybody. Thank you. My name is Yann Guyot. I'm in charge of mathematical modeling and climate change adaptation of the poultry sector. And I was in charge in this project to try to find a way to better know what's going on within the truck during heat stress. So we decided that since we were following and monitoring a lot of transport, to switch to mathematical modeling to have a better overview of what's going on during transportations of broilers. So can you please switch, Pauline, to the next slide? So I have a question for you, which is that we call for your intuition. According to you, in the truck, where is the hottest part of a truck during a hot transport? Do you think it's at the rear, at the middle, or at the front, close to the cabin? So basically, just to know if your intuition about that. Yeah. So most of you will see has a good intuition or a good knowledge about it, as you will see in the presentation. Well, so as you know, there is millions of broilers transported globally and potentially in stressful conditions because of heat and because of hot weather. That might lead, as Laura said, to DOA and eventually, of course, to economic loss. But before DOA, it can also lead to weight loss, according to if the duration is quite long, or maybe meat quality degradation. And also, again, as Laura has mentioned before, it can lead to several animal welfare harsh condition. And this condition will happen a lot more in the future because of climate change and global heat rising. Heat stress will happen a lot. For example, this summer we had in France, we know that we cannot transport animal during daytime, but at night we had 30 degrees at midnight. So we know that this kind of conditions happens already, and it will happen a lot more in the future. So we have definitely to tackle this issue in the future. Next slide, please. So the question we have is that can ambient condition be estimated within the truck, first of all? So of course we can set sensors, but can we do it without sensors? It will, of course, lead to reduce the cost because sensors are the cost and you have to check the weather and everything. And it will be time saving because, of course, again, checking everything takes time. The other question we have is how we can extrapolate the measured temperature to all birds, because we will put sensors. Maybe we put one or two sensors. Maybe we put them at the rear, the middle, or the front of the crates. But what's happening away from the sensors? So we think that we need to have a more comprehensive knowledge of the heterogeneities that are happening within the truck. And another question is that what would be the air velocity distribution within the crates, the containers themselves? And there is sensors for that, but we think that they are not very suited for monitoring during transport. They are very sensitive sensors, and they might be very quickly destroyed by the animals. So we cannot, I would think that we cannot easily assess velocity, and it's a very key parameter for heat stress. So this is what leads us to the idea to use mathematical modeling to know what's going on during transportation, and especially CFD modeling, which stands for computational fluid dynamics. So please, Pauline, merci. Thank you. So basically, what is CFD? So CFD basically just solve the equations of fluid transportation and temperature transport distribution within a given set or given medium, let's say. It's broadly used almost everywhere in engineering. It's used in biomedical, so you can simulate the blood flow within the heart, for example. It's also very used in ventilations, like if you design a new room, if you design an hospital or whatever, they will always get what will be the best and the optimal configuration of the building to have an optimal comfort for the people. It's one of the big one is used in aerodynamics. When you make a car or a plane, they always use that, or even urban planning now they are doing to make the cities for heat stress more comfortable. So we use this method, and we have to set some specifications to our problem. The first one is that we cannot simulate every animal within a truck. There is almost 7,000 animals. We cannot design all of them and calculate the airflow passing through them. So we consider them as a porous medium. I will not get into details, but it's very important characteristic. And this porous medium will reflect the capacity, the ion capacity of the broilers to let the fluid flow pass through them. So there is a parameter for density and a parameter for body weight. And also, so this is for the fluid flow itself, but it's another specification is that we have to consider the broilers as heaters, because they are heaters basically, like we are. They emit temperature, they emit heat, like us, they emit heat in two forms. The first one is the sensible. So the sensible is the heat that will rise temperature. And the second one is the latent heat, which is basically for us it's sweating, but for animal it's hailing. Not hailing, sorry. I lost my word. Panting. It's panting, and they will generate humidity and water in the air. So we have to take the specific behavior in the model in order to be more accurate. Next slide, please. So here are the results of one of the simulations. So you can see it's a truck driving within 60 kilometers per hour on average, for example. And here you have your answers. So most of you were right. The hottest part is on the front part. As you can see, you have the temperature map, which it's a map basically. It's in 3D. You have the temperature map within the containers. You have the humidity map within the containers, and you also have, since it's CFD, you also have the fluid velocity itself. And the reason why the front part is the hottest part, it's because the airflow is touching, basically it's touching the truck in the middle, and it creates a very backward stream that will push the heat back to the front, at the front. So the animal, there is very, very few velocity there, and they are getting the heat from the others. So that's why it's very, very less, it's the harshest place in the truck is the one in the rear and in the bottom, as you can see here. Okay, so that's the hottest monitoring we had. So we had them for like something like 14 monitoring of transport. And of course, we had to validate the model before using it as an assessment tool. So first of all, we collected data. So we collected data from waiting at the farm to the slaughterhouse, and you can see here on the temperature that we have this. We have sensors at the front, sensor at the middle, and sensor at the rear. And so the rear part is the one that is loaded first, of course, because containers are loaded this way. So this is the part that the temperature increases at the beginning. And you can see that. So what we did, that we took, and then since we are modeling only steady state conditions, we take the average the average temperature and humidity over driving as the one what we want to against the one we want to validate the model. So as you can see on the picture on the top right, basically we are simulating quite well temperature with a good approximation and a little less humidity, which is normal because we always expect humidity to be less estimated because of the capture sensitivity and everything. But we are quite happy with temperature and prediction ability of the model. So now we have a model that is able to have a 3D map that we can rely on the data on the outputs. So it gives a 3D map of the temperature. So and the humidity, how we can transform this physical data that we are simulating into a thermal stress indicators, because we have to gather them together. So next slide, please, Pauline. So the EFSA provided in their journal two indicators. So I just selected the ones because they are mostly the same, basically. And these two parameters um, are dependent on temperature and humidity. We should never forget humidity because, for example, for you, if it's 37 degree and 30% humidity, you feel hot. But if it's 37 temperature degree and 100% humidity, we all die in few hours because we cannot regulate our temperature. We cannot evacuate the heat. So it's always a combination of both. And what they do is that they provide this apparent equivalent temperature, which is heat stress indicators. But if I follow this AET in my truck, what I can see, for example, for the hottest monitoring that we had, is that 80% of my animals are in danger and 20% of my animals are in alert, and none of them are safe. So what we would expect is that in such harsh condition, we should expect a lot of DOA. And actually, please, Pauline, this is not what happened. As you can see here, the hottest monitoring, so the one with 80% animals in danger, the dead on arrival were not higher than any of the ones that we monitored, with very few dead on arrival and in not called mild conditions. So the question we had is that we think that in these indicators, two factors that are not taken into account might explain this discrepancy. The first one, as I said before, is the air velocity, because it's very important. You can imagine for you as well, if it's hot, then it's hot, but if you have a little wind, you feel much better, or if you drive a motorcycle and this kind of thing. So air is very important. And the other one is exposure time. If the animals are exposed 10 minutes or 2 hours, it's definitely not the same. So we think that without taking these two parameters, the indicators we have are not good and not enough to assess it. So please, Pauline. So how to take them into account? The first one, so the air velocity, from the literature, from a paper from Birg et al., they designed what they call an effective temperature, which could be like a felt temperature, and it takes into account temperature, humidity, and velocity, and it calculates according to these three parameters. It calculates the body temperature rise, because the real definition of heat stress, this is body temperature rise. It's like for us, it's the same. If temperature increase, so an animal, a broiler is around 41 degree on basic. But if temperature rise, after 1 degree, it will have a problem in terms of performance. But after 3-4 degrees, we know that death will happen. And these indicators, it's also very important because, and very well made, because it takes into account that if the air temperature gets close to the body temperature, you can blow as fast velocity as you want, you will not decrease. You can also imagine that for you. If we blow very hot air on you, if you feel hot already, it will not get you colder. So, and it will not cool you down. So that's something that is taken into account in this indicator. And the other one is the body increase depending on time. So as you can see on the 3D graph here, if you have effective temperature, let's say around 32, so on the left of the picture, then you can face this effective temperature forever. You will remain in the green part. Your body temperature will remain below 1 degree, so it's fine. But then if you face 40 degree of effective temperature in 2 or 3 hours, in 2 hours, the animal will be dead. Basically, yeah, the body temperature rise will be so high that death will happen. So now we think we have a tool, an indicator taking the 4 parameters together, and we want to check now in our hottest monitoring, is it going to show that this DOA we had, which was lower than the others. So please, Pauline. So this is the one, our hottest monitoring. So you can see the ET. So I forgot to put ET. So the effective temperature is displayed on the top left. And you can see the animation on the right. So the one on the bottom is just the increase of body temperature. So 0 means no stress. They will remain the basal temperature. And then you can see at the rear part, always this part, the animal will start to have an increase of temperature. But what you can see on the bottom left picture is that at slaughter arrival, most of my animals, the animals of this monitoring, were still in the good conditions. So it explains way better the dead on arrival that we have seen, the below one. You can see most of the animals are not in danger, are not in alert in these conditions. They are just fine. Okay. So now we think we have a tool that is working. We can make simulation, extrapolations. What will happen in the future? What will happen if my conditions are like this or like that? So we simulated here, like as I told you, one of the conditions we had in France this summer, which was 30 degrees at midnight, 40% humidity, and we tested it. We tested what will happen. And what we saw is that after 1 hour, not even before, some animals start to feel some stress again, the real ones. And between the first and the second hour, we have animal starts to feel very bad, like the temperature, the let's say the body temperature more than 2.5 degrees more than the basal, which starts to have stress. Very good big one. And then after 2 hours of transport in these conditions, the red are coming, which basically will lead to DOA. So we know that in these conditions, after 2 hours, problem will occur. So okay, fine. So what can we do? So we can switch to some levers. Since we have a tool, a simulations tool, sorry, we can test some stuff. So the first one is say, go Pauline, please. The first one says, if I reduce the density by 10%, like it's usually applied, what will happen? So you can see that at the beginning, you have exactly the same stress distribution within the truck, a little bit lower, but it can be better to have this sort of density for long trip, because at 3 hours you can see that you have way less animals in very harsh conditions than without applying the 10% density reduction. But another one, since the problem always occurs at the front, can I just leave these containers empty? And the other ones, all the others, with the same density as before. So this is what we applied here. And as you can see, it's a better condition than just reducing density overall. Because even after 2 hours, you have very few animals in small heat stress, and no red is appearing. Actually, we wanted to try. I'm trying now that if I remove only the bottom one, I'm testing it right now to just remove the bottom one if it's even better. And also the good point is that you have better condition and you transport more animals, because removing 2 containers over 22 containers, it's 9% reduction instead of 10%. So more animal, better conditions. So we think that is the best solution one of the best solutions will be this. So as a conclusion of this work, we think that now we have a tool capable of quantifying the thermal stress, which are based on weather condition. We can simulate different weather conditions. The loading, we can change the density, and traffic, because now I simulate, let's say, average velocity of 60 kilometers per hour, which is normal for a truck. But what happens if it stops? What happens if it has to drive it like traffic jam? It has to drive for 10 kilometers per hour. Like, I think condition will be way harsher. And also we think that this tool can provide recommendation and mitigation strategies. Of course, some future work still needs to be done. So we want to incorporate variations in driving speed. So basically, as I told you, this model can, as we think, easily extend it to other conditions than just driving. We want to test it on the waiting time at the slaughterhouse. So the animal will be stuck, maybe some fans, some big fans, and check and everything can be done. So it's just the same, just geometry change. So we want to, we are already multiplying monitoring to add more weight to the model. And of course, we would like to see the mitigation strategies we provide, we advise in the real transport to say, okay, what you told us, it's indeed more efficient. And the last one is because this type of modeling requires some expert hand to make it and to make the simulations. And we are thinking about how the output of the simulations can be provided to the people and to the people engaged in boiler transports. Either within like a chart of, or maybe a meta model. We are thinking about it right now, so how to provide it. I can see that there is some questions in the chat. So we have one of the stakeholders, part of the aWISH project, had recorded some question and some ideas and what she thinks actually about this model. But I think we can already answer the question in the chat, Pauline.